Hey guys, you caught me solving the Rubik's Cube. Now, the Rubik's Cube is a fascinating mathematical puzzle. There is a ton of math and algebra involved in solving the Rubik's Cube. Now, we're not going to go into that today, but I do want to use the cube as an example because algebra is full of comparing and looking at the relationship between two variables. And this next unit is going to look at how two variables relate to each other in a direct and inverse way. So take example, my 2x2 Rubik's Cube. It is a little bit smaller because there's only two cubes on each edge. But if I jump up to the 3x3 Rubik's Cube, you'll see that it's a little bit larger, right? The surface area is a little bit larger because, again, we have three cubes on each edge. Now consider the 4x4 Rubik's Cube, even larger yet. So you can tell, because now we have four cubes on each edge, that the surface area of this 4x4 will be larger than the surface area of the 3x3, which is larger than the surface area of the 2x2. So when we consider these two variables, the edge length and the surface area, we say that these two variables are directly related. And that's what we're going to be talking about today. Let's start off by reminding ourselves what a direct variation equation is. In an equation that relates two variables, if the variables both increase or decrease together, then we say that that is a direct variation equation. So, for example, the edge length of our cube and the surface area. Let's take a look at the circles. We know that a circle's area formula is pi r squared. As the radius increases, so also will our area. So our first circle will have an area of 4 pi. Our second circle with a radius of 3 will have an area of 9 pi. And our third circle will have an area of 16 pi. And finally, our fourth circle will have an area of 36 pi. You can see here then, as our radius increases, so did the area of this circle. So we call this a direct relationship, but we say that A varies directly as the square of R, or that A, the area, is directly proportional to the square of R. Now, let's talk a little bit about the general form of the equation for direct variation. It takes on the form y equals k times x, where k is the constant of variation. Now, the constant of variation is like the rate of change. In example 4, we have the surface area S of a cube, and it is directly proportional to the square of the length E of its edge. So this is just like our Rubik's Cube that we started off with. Now, we're also given that a cube with edge length 5 centimeters has a surface area of 150. So let's start off by identifying our independent and our dependent variables. Our independent variable is E, the edge length of that cube. As it changes, the surface area will depend on the edge length. Now let's write a direct variation equation. Remember, it's our dependent is equal to the constant of variation k times the independent. And since it's our independent, E squared. Now let's see if we can determine what the value of k, our constant of variation, is, by substituting in our known values for E and for our surface area. So we'll say 150 is equal to k, our constant of variation, times 5 squared. 5 squared will simplify to 25, so we'll say 150 is equal to k times 25. Now we'll divide both sides by 25, and that gives us a result of k equals 6. So 6 is our constant of variation. Now we're going to rewrite our direct variation equation to say surface area is equal to 6 times E squared. And now we can finally use that equation to find the surface area of a cube with an edge length of 8 centimeters. Simply by substituting 8 in for E, when we square 8, we'll get 64. 6 times 64 will result in 384. And now it's our surface area, so this will be centimeters squared. All right, in example 5, we have another situation which m varies directly as the fifth power of p. So I'm going to write a direct variation equation that relates these three variables. M is my dependent variable, is equal to k, the constant of variation, times the independent to the fifth power. So that's p to the fifth power. Now let's substitute in one known set of values. 96 is equal to k times 2 to the 5th power. 2 to the 5th is equal to 32. We'll divide both sides by 32, and therefore our constant of variation is going to be equal to 3. Now we can take that constant of variation that we know and rewrite our direct variation equation. M is equal to 3 times p to the 5th power. Once we have our direct variation equation, we can use it to solve for any value of p. M now should be equal to 3 times 5 to the 5th. 5 to the 5th will result in 3 times 3,125. And therefore our result for M when p is equal to 5 should be 9,375. All right, one final example here. Again, we have another direct variation situation. You should be getting pretty good at recognizing what our independent and dependent variables are. This will allow us to write our direct variation equation. Y equals k times x to the 3rd power, which is cubed. Substitute in our values that we know, and we can find our value for our constant of variation. So 48 equals k times 8. Divide both sides by 8. 48 divided by 8 results in 6, and therefore we can rewrite our constant of variation equation, our direct variation equation, y equals 6 times x cubed, and now we can substitute in our known value for x, which is 7, so 6 times 7 cubed results in 6 times 343, and that gives us a value for y of 2,058.